Hello, everybody, and welcome back to this seminar series. So today we have the pleasure to have with us Irene Valenzuela, who is currently a member of the theory department at CERN, and she worked at several universities before, like Harvard, Cornell, the Max Planck Institute in Munich, and she did the PhD in Madrid, and her research is very interesting because it includes string theory, theoretical cosmology, particle physics, and today she will talk about this Swampland program. So thank you again for coming, and please, yeah.
Okay, so, well, thank you very much for the invitation and for organizing this online series of seminars, lectures. I hope the students are enjoying it. Today we are going, the plan is to drive you through a journey, starting with the basics of the Swampland program. I will be speaking in English because I think not everybody is native, but I'm happy, like if you want to ask questions, you can both ask in English or in Spanish, whatever you prefer. And also if I say something and you don't understand it, please just say it. Okay, I can repeat it as many times as necessary. And if you have any question, whatever question you have, doesn't matter how basic or dumb, stupid might look to you, just do it, okay? The more interactive is always the better because there are no stupid questions. We are here to learn. So, the Swampland, okay? So this is the topic of today. So, let's start motivating what is the Swampland program, okay? Now, when we work in theoretical physics, okay, something that you might have already learned about, otherwise I'm sure you will at some point, is that we always define effective field theories, right? In the sense that we are interested in describing the physics at some energy scale, and then we describe this in terms of an effective field theory, which is valid up to some cutoff, okay? Without worrying too much about what happened in the UV. Now, the point is that when you learn about effective field theories, you know that you can describe some theory which is at a high energy scale, the UV, okay, that's what I'm putting, high energies, and you can, in order to have an effective field theory at a lower energy scale, you can integrate out the degrees of freedom. Okay, so we can describe different effective field theories that are valid at different energy scales. So for instance, maybe we can have a theory which is valid at the electroweak scale to describe some particle physics, or maybe we are interested in the cosmological constant, or maybe we are interested in quantum gravity. So these are all different scales, and we can have different effective field theories that describe the physics at these different scales. And the procedure of moving in this energy flow is what is called this integrating out the fields. Okay, you integrate out everything that is heavier than a given energy scale, and you obtain the theory in the infrared at low energies. Now, this is something that can always be done, okay? But the question is whether you can do the opposite. Whether if you start with some effective field theory that describes the physics at low energies, like for instance for particle physics, can you always UV complete the theory at higher energies in something that is consistent? Okay, and this is the key question that is behind the Swampland program, okay? Whether theories can be UV completed. Okay, for instance, if we have the effective field theory of atomic dynamics, we can describe how the atoms work. Then we can go to higher energies, so smaller distances, and complete the theory by understanding what happens inside of the atoms, right? Like the electrons and so on. Now, you can continue and then have nuclear physics, and you can continue, you have the quarks, and then you want to go beyond that, we want to go beyond the standard model, we want to go to higher energies and continue completing this theory, okay? Like understanding what happens at higher energies. But when you work, for instance, in particle physics, and I say, okay, I'm gonna add the standard model plus, I don't know, this dark sector or something else. The question is, is this still a consistent theory? What things can I add so that I can guarantee that I will always be able to continue to higher energies? Okay. Now, the point is that even if from the UV you can always go to the IR, from a given theory in the IR, you cannot always go to the UV. Okay, so the message is that not every EFT, even if it looks fine at low energies, can be UV completed in a consistent theory. Okay. And in particular, this is something that already happens in quantum field theory, but it's very strong if we are wondering, if we are interested in quantum gravity. Okay, so in particular, not every effective field theory can be UV completed in a consistent theory of quantum gravity. So what do I mean? To make it clear and say that if my IR theory, I have some Lagrangian, some EFT, that it has some renormalizable couplings, plus all this tower of non-renormalizable operators. So this theory is valid up to some cutoff lambda. If you go above energies beyond lambda, then you have to UV completed. Good. Yeah. So the message is that first, this Lagrangian cannot be whatever you want. There are constraints that appear there. And also, of course, in the tower of non-renormalizable operators, there are also constraints that appear if you want to UV complete it to a unitary theory. Okay. So the goal of the Swampland program is to determine what are the constraints that an effective field theory must satisfy to allow for a UV completion in quantum gravity. Okay, so this is saying that even if quantum gravitational effects seem to be important at very high energy scales, still have an impact, can have an impact in the infrared at low energies, because not every theory that you construct can arise as a low energy limit of quantum gravity. Okay, so the picture that we usually plot to represent this is that if we imagine that we put in the vertical axis the energy, and then we have like this space of possible EFTs. So in this plane, all these are possible effective field theories that I could construct following the rules of quantum field theory and so on. Each point is like a different EFT, okay? The point is that not all of them can be UV completed. Only this subset, which we call the landscape, can be UV completed. And those theories that cannot belong to the Swampland. Okay, this is UV completed in quantum gravity. So this is inconsistent with arising from a quantum gravity theory at higher energies. And this is consistent with quantum gravity. So this is where the name comes from. So the Swampland, right? It's a funny name. It's like Ciénaga or Pantano. And it was formulated by Qumran Baffa years ago in opposition to the landscape, because the landscape was the typical word that was used to define those EFTs that arise from quantum gravity, in particular from string theory. Okay, so this is like the main goal. We try to understand what distinguishes the landscape from the Swampland. Okay, so what are the constraints that we need to satisfy so that we belong inside of this cone. Okay, and I'm putting a cone because these constraints typically are more important as you increase the energies, so they become more restrictive. Okay, and in particular, also all these Swampland constraints, okay, that we need to satisfy disappear if we send them Planck to infinity, if we decouple gravity. Okay, it's like saying that the cone would go infinitely high up, so in the end expands everything. So it's very important that all these constraints that we are talking about they really refer to a UV completion in quantum gravity, so they disappear if gravity is not dynamical. And that implies, for instance, that they only apply, to be conservative in dimension of the space-time bigger than 3, okay? Because for less than 4 dimensions, gravity is more tricky. It behaves more like a field theory. And in fact, for instance, in 2 dimensions, you don't have black holes. So there's no dynamical gravity. So these constraints do not apply. Okay, any questions so far? Okay, so this is the goal. Try to classify, like to distinguish what can arise from quantum gravity, what cannot. Why? Well, I mean, of course, this is interesting to understand quantum gravity itself, but it's also useful for phenomenology, because if you are able to determine these constraints, then you can give phenomenological implications, right? You can use these new rules of the game to construct effective field theories, logical implications. So they are like guiding principles, like new rules that you have to apply. And they are very related to naturalness issues. So maybe you have heard that we have this cosmological constant problem, electron-weak hierarchy problem. Basically, we observe experimentally some quantities like the Higgs mass or the cosmological constant that are smaller than what one would expect, which implies that the theory seems to be more sensitive to the UV than what one would imagine. And these Swampland constraints, they are putting non-trivial constraints in the infrared coming from the UV, can shed new light into all these naturalness issues. Because maybe what looks natural from the low energy perspective is not natural from the UV, and vice versa. So you have to change this logic of naturalness.
Sorry, can I ask a question?
Yes.
I didn't understand very well. What does it mean exactly that a theory is UV completed in quantum gravity? I mean, you have some theory that is, well, let's say defined in RF limit or scale, and then there is some definition of UV computation. Can you repeat this kind
of? Of course. Yes. So let me do it in quantum field theory first. So the point is, if you can have an effective field theory, which is valid, for instance, up to some cutoff one that can be, I don't know, 3 giga-electron-volts, whatever, some energy scale. Okay, so this is able to describe the physics up to that scale. Above that, then there could be new physics, like new particles and so on, that you have not included. Okay. Now, imagine that we continue doing research, right? So now you complete the theory in the sense that when you continue going to higher energies and probing what happens there, it's not that the previous EFT is wrong, it's that you complete it in the sense that you add new physics, right? That might arise, maybe you discover a new particle. So you have a new EFT. So this is EFT1, this is EFT2. Okay. That now it's valid up to some cutoff that is bigger than the original one. Okay. So we have completed, like we have extended the theory to probe higher energies. Okay. Now, the question is whether, if we just have information about this one, whether we can guarantee that there will be some consistent way to arrive to some EFT2, okay, like to complete the theory, to arrive to something consistent. Now, this might seem obvious, but the point is that it's not always possible. Like, for instance, if you start, to give you one example in quantum field theory, if you have some scalar field, let's put some scalar, and you have some, this is like some quartic derivative operator, you could think that here, this lambda, this coefficient, can take any value. I mean, then in principle, there is nothing wrong. But when you study UV completions in quantum field theory, you can show that if now I go to higher energy, so that this becomes from integrating out some states, and it's not a non-renormalizable coupling anymore, I have a new EFT2. Unitarity conditions, like requiring that this theory is unitary and causal and so on, imply some definite sign for this lambda. So if this lambda was negative, it would never be possible to complete it to a higher energy theory. So that theory is not consistent. It doesn't make sense.
I want to ask some question.
Say again?
What guarantees that this quantum gravity is a field theory?
Okay, so now, so this is for QFT, okay? So this is a question of whether you can UV complete it in QFT. Now, what if I require not only that I have QFT, but that this is actually a quantum gravity theory? Okay, so what And this is what the Swampland program is about. So it's about understanding what I need to satisfy, what constraints I need to satisfy in this CFT, that is weakly coupled to Einstein gravity, so that it can be completed at higher energies in a full quantum gravity theory, which is unitary and so on. Okay, and this is what the Swampland program is about. When you specify that the completion has to be in quantum gravity. Is it clear? Okay, so another way to say it is like we have all these EFTs. Let me add here the addition. So they are weakly coupled to Einstein gravity, right? Okay. But they are quantum field theories.
It almost was clear. Just okay, I understand the UV computation. Yeah, you mean that it's a way to say that if a theory can be defined in a higher level energy, let's say. But in quantum gravity, I mean, what means this part of the sentence? UV computation in quantum gravity, the part of in quantum gravity.
It means that it has to be completed in a theory that is able to describe gravity at a quantum level.
So it means that this theory has to have gravity.
Exactly, it needs to have, exactly. So imagine, okay, if I have a quantum, so these are like quantum effective field theories, okay? Now, these quantum effective field theories, they don't have quantum gravity. This is like the graviton, you can couple to Einstein, but it's classical, like it's classical gravity, okay? So you have a QFT in a classical background. Now, I want to complete it in a theory that is able to describe the graviton at the quantum level, like a quantum gravity theory.
I see. Thank you.
Okay. And then that's not necessarily always possible. Okay. So that's the point. Like you can start with a QFT coupled to gravity at the classical level, but if you now want to promote this to the quantum level in a full quantum gravity theory at higher energies, maybe you find that it's possible or not, depending what is the theory you started with. And that's what we try to understand, how to guarantee that we can complete it in quantum gravity. For example, the obvious example that you could imagine here is anomalies, right? Like you can have a theory which is coupled to gravity at the classical level. Now, when I promote it to the quantum level, I could have an anomaly that makes the theory inconsistent. So I need to require that the theory is anomaly-free. That's a condition that you have to imply to be able to promote it at the quantum level. What we see and what I am going to show you today is that requiring that the theory is anomaly-free, like there are no gravitational anomalies, is not enough. There are other constraints that you need to impose to guarantee that you will have a consistent description of this theory together with gravity at the quantum level. Okay, shall I go on? Okay, so that's the goal. Like this is the goal of the Swampland program, to understand this question. Okay, so to understand what are these constraints. Now, as I was saying, it's interesting because, yeah, sometimes these constraints go beyond anomalies, so there are new rules that we have to impose, and that's why this has been a lot of activity in the Swampland program in recent years, because it's like it's having new information, like adding new rules to the game. Okay. And these new constraints that appear sometimes are very surprising from the QFT low energy perspective. Okay, so just to give, maybe let me put it here. Okay, let me put it here. So sometimes these are surprising. So the examples we are gonna see is that, for instance, there are no global symmetry. So having a global symmetry is something completely fine in EFTs. But once we include gravity at the quantum level, it seems that they are not consistent. So you need to impose that you don't have global symmetry. So they are like surprising constraints that you cannot imagine if you just work at low energies. And also small gauge couplings. Okay, having a very small gauge coupling, in principle, is completely fine in QFT. We even like it because you can do perturbative computations and it's fine. But we are going to see that this is actually too close to restore a global symmetry, and they are problematic if you want to have it in a theory of quantum gravity. And the same with large field ranges and many other things. Okay, so these are problematic if gravity is described at the quantum level. Okay. So let's see in a quantum gravity theory. Okay, so how do we that? How do we find this type of constraints? Okay, it's a very ambitious program. I mean, it's a very difficult question. And what we try to do is to get evidence from as many research areas as possible. Okay, so very important is string theory in the sense that regardless of whether string theory is the quantum gravity theory that describes our universe, is a consistent theory of quantum gravity. So you can use it as a theoretical laboratory to try to extract what conditions are required by quantum gravity consistency. Okay, so we learn a lot from string theory, like trying to extract patterns from that, and then try to understand if we can motivate them also independent of string theory, because the whole game, I mean, the tricky part here is to disentangle what properties are maybe model dependent and they are only in string theory, and which ones we think are more general and are required by quantum gravity consistency. So in order to do that, you also use a lot of information about black holes. We'll see several arguments based on black holes. You can also think more generally on holography, because the CFT is very useful to prove of some of these constraints at a very quantitative level. And you can also think of like a matrix bootstrap in the sense that you impose unitarity and causality constraints, right, to the UV completions and try to see what this unitarity and causality imply at low energy. So these are all different approaches that you have. And it's only when we have some pattern that we find evidence for this pattern from different approaches, like both from string theory, from black hole physics, holography, and so on, that then we think that we promote this pattern to a conjecture, and we believe this is a general feature of quantum gravity. Okay. Any other question? Okay, so doing this in the past years, we have several proposals about what these new constraints could be, which are described by these Swampland conjectures. Okay, so most of them are motivated from string theory, but there has been a lot of work trying to find also arguments beyond that. Okay, and it's all ongoing. So this is a program which is very active nowadays, very recent. You will see a lot of research, which means also that what we know now from what we learned in the following years would also change a lot. Okay, so this is something which is quickly evolving and changing very rapidly, and that's why it's something interesting to learn now, because if you want to collaborate and get into it, it's a perfect moment. Okay, so these are like some web. So I put here like some of these conjectures. I'm gonna describe just 3 of them, which are really the basics, like the core of the Swampland program, which are no global symmetries, the weak gravity conjecture, and the distance conjecture. Now, these 3 are very important, and everything else that you might hear are actually related to these 3. Okay, so you might hear about coordination conjecture, completeness hypothesis. All these are actually, we have shown in recent years that are the same conjecture, they are related. So the whole goal here is also try to reduce all these constraints to the minimal number of statements that would reproduce everything. And for instance, these 2 are the same now, okay? This is also like, I would say this is also the same at the topological level. This is a generalization. And these other here and others that I didn't write are kind of consequences of the previous ones, okay? So let's focus on these 3. And at the end of the lectures, if you have any question about others and so on, we can discuss more. Okay, very good. So let's go. So far it's been like very vague. I'm just telling you that there are constraints that we need to satisfy. to be UV completed, like to be consistent with quantum gravity. What are these constraints and what is the evidence for them? And what are the implications? So the first one that we are going to talk about, which is the most important one and also the best established one, is the absence of global symmetries. Okay, so the statement is that any global symmetry must be either broken at some energy scale or gauged. So I cannot have pure exact global symmetries. Okay, now when describing this, it's very important to understand well what is the difference between being a global symmetry and a gauged symmetry. Okay, and with gauged, I don't mean the local redundancies. Okay, I mean the global part of the gauge group. So the electric charge, for instance, is a gauged symmetry. It's associated to some gauge degree of freedom, but still is something physical. It's a symmetry. I have a conserved charge that I can measure, but it's not a global symmetry. So I'm gonna try to explain the difference. First, I'm gonna give you some intuition and to understand the difference even without doing any computation. And then we will formulate it more properly and see how we actually work on this topic. Okay, so what is the intuition? Well, the intuition is that the difference between global and gauged is that global charges, so whenever you have a symmetry, what you have is some conserved charge. So global charges cannot be measured.
Can you repeat why global symmetry is bad in quantum gravity? It's something.
I didn't say it yet. Don't worry. You missed it because you're missing it because first I'm gonna tell you how to understand the difference between global gauge to make sure we are on the same page, and then I will tell you why that's bad. Okay, because also this intuition is useful to understand why the global symmetry is bad in comparison to a gauge symmetry.
So if I'm starting with the field theory, means which already has a global symmetry.
Mm-hmm.
So means now I want to go to I want to check whether it will leads to quantum gravity or not. I have to break that symmetry by adding another field. Huh?
Mm-hmm. Yes, exactly. So you have to either break it or gauge it. In both cases, you need to add new fields.
So what will be that new field? Means it will always be a graviton, or means how will you come to know about that external field?
Yeah, that's a good question. That doesn't have a universal answer. Now we are gonna see. Okay, so first we have to motivate why we cannot have the exact global symmetry, and then you can ask, okay, but how is it broken, right? Like what is the scale, right, at which it's broken? Because that's very important for phenomenology. This is about quantifying the breaking. There has been recent works that, are proposing some minimal breaking that must happen because of quantum gravitational effects. But sometimes it can be even stronger. Okay, it's just like a minimal breaking. That's at the very least, just the existence of black holes and processes that change topology, like wormholes and so on, are gonna break the symmetries. So this already gives like an exponential separation on the operator. There is like a minimal breaking that you're gonna have for sure. Now, there's a lot of research now going on trying to understand when you have only this minimal breaking and when you have even stronger breaking. Because that would be great to know, right? But there's no universal answer yet. Like this is ongoing research. Okay, we'll also see that actually like the weak gravity conjecture and the distance conjecture are also a way to quantify how much you have to break these symmetries. Okay, but this will come later. Okay, so intuition. Now, just for everybody to keep in mind, so global symmetries are conserved charges that you cannot measure from far away, okay? So for instance, I give you two examples. If I have an electric charge, okay? Like for instance, I have the standard model of particle physics and I have some process. The electric charge is conserved, right? It's a good symmetry. This is one symmetry of the standard model. And I can also have another symmetry of the standard model, which is called B minus L, which is the number of baryons minus the number of leptons. This is also something which is conserved at the level of the standard model of particle physics. So these are two types of symmetries. But B minus L is a global symmetry, while the electric charge is a gauged symmetry. Okay, both are symmetries, both act on the Hilbert space, but B minus L, there is no way to measure this like from far away. Like if I have my LHC, in which I have the particles colliding, right? I can detect the electric charge because I can have a Gauss law and measure the charge from very far away because I have the electric field that carries the information far away. But for B minus L, there is no way to know what is the result of B minus L unless I really go there and count how many baryons and how many leptons I have. Okay, I cannot carry that information far away. I don't have a dynamical example gauge field to carry that. Okay, so these ones are the ones that I cannot carry information are problematic in quantum gravity. And there are several ways to argue for it. From holography, I mean, there are some proofs from holography which are basically based on this, because if you cannot carry the information to the boundary, you're going to get an inconsistency with the correspondence. Okay, that's why I like this intuition. But also from the perspective of black holes, you can also give some motivation. Okay, so that is how everything was formulated originally. So if you have a black hole and the black hole is not charged around some gauge field, okay, it's a neutral black hole, you can write what is the solution for the black hole. I mean, it doesn't matter the equation I'm writing, it just to make it concrete, but what I want to say is that the solution for the black hole horizon just depends on the mass. Okay, this is the mass of the black hole. And if I now imagine that we have B minus L, which is exact. Imagine that would be something exact of our full theory. I could now throw some particles, some baryons in my black hole, so that I change the black hole gets charged under this global symmetry, has some number of some value for B minus L. Okay, but this value does not change the black hole solution. Okay, the horizon is blind to the global charge. And that's related to the fact that you cannot measure from far away. Okay, so the horizon, I mean, what we see from the exterior, is completely blind to the global charge, which means that you can actually throw, if I have the black hole, you can throw many different particles with different values, for instance, of B minus L, and construct many different black holes that a priori you would say they are different because they have different values of the global charge, but they look the same from the exterior. Okay, so we can construct an infinite number of black hole solutions with different values of the global charge that look the same from outside. Okay, and this is problematic because this is actually going to give rise to an infinite entropy. Okay, so what is the entropy of the black hole? Basically, the entropy is, roughly speaking, all the different ways you can have to construct the same black hole. It's like the different constituents. So if you have infinitely many ways to do it and have the same black hole horizon, this is going to give rise to an infinite Bekenstein entropy, which is inconsistent with what we know about black holes, that they have a finite entropy, which is related to the temperature and the size of the horizon. You could also do arguments based on remnants, like saying you will have now infinitely many black holes that are stable, they can be degenerate, they are going to spoil the effective field theory and so on. But basically, I mean, the problem comes from the fact that from the exterior, you cannot measure this charge. Okay. Any question? Okay, so this is a heuristic motivation, okay, that gives you an intuition of why global charges are problematic. But of course, the reason why this conjecture is so important is not only because these heuristic arguments, which are not proof, but because of all the evidence that we have also gathered from real quantum gravity theories. Okay, so in string theory, there are no global symmetries. You can prove it at the perturbative level in the worksheet. This is already done in the Polchinski book. Okay, and you can also prove it in IDSCFT for splittable symmetries, precisely of what I told you, that you need to be able to carry the information to the boundary. Okay, And also more recently, there has been many works that try to relate the absence of symmetry to unitary of the black hole evaporation process. Because I don't know if you heard about it, but there has been a lot of activity reproducing this page curve, like how the entropy changes as the black hole evaporates, using wormholes and topology changing processes. And the point is that these same wormholes, these same objects that you need to explain the unitary black hole evaporation are also breaking the global symmetries that you might have. Okay, so both things are correlated. And in general, yeah, whenever you have some process that changes the topology, it's going to break a global symmetry because we're going to see that global symmetries are actually associated to topological operators. So they need to have a fixed topology. Okay. So let's go on. So I'm not gonna, just because of the lack of time, I'm not gonna explain in more detail all these different proofs. You can check at the beginning of the lecture, I put you some reference. I didn't say, but I have some lecture notes about the Swampland program. So if there is something that you want to learn, I mean, that I don't have time to explain, you can always take a look there and look for references. And otherwise you can ask me later. But for the moment, let's just leave it here. And what I'm gonna do to finish this is to give you some examples, okay? So let's try to make it concrete. And give you some examples and some more proper formulation of these global symmetries to understand what are the implications that it has for the EFT. Okay, so I give you this intuition, this blah blah, like global charges cannot be measured from far away, but like, there is a proper way to formulate this in quantum field theory, which is based on topological operators. So I'm just going to explain it quickly. Just because it's also something that is very important this year, so I guess it's also good for you to learn it, even if it's not super essential for the Swampland program, but it's very useful. We use it all the time, this new language. So how do we properly formulate this intuition that global symmetries are not measured from far away and are different like symmetries? Well, we do this in terms of defining some topological operator. Okay, so a global symmetry must satisfy 3 requirements. Okay, so this is a formal definition. First requirement is that it has to be a transformation of the theory that is conserved, right? So saying that it's conserved is like saying that commutes with the Hamiltonian in quantum field theory, which it means is that it commutes with the stress energy tensor. Okay, so this is, let me write it here. So this is to require that the symmetry the charge is conserved, it's an exact symmetry. And saying that commutes with the stress energy tensor is equivalent to say that if you apply some continuous deformation, like some diffeomorphism, nothing should change, like the theory should be invariant, which is equivalent to say that this operator that parameterizes the symmetry, my transformation, is topological. Okay, so that's why when we say that a symmetry is described by a topological operator, is because we want that is invariant under small deformations, continuous deformations, because we want it to commute with the stress energy tensor, because we want it to be conserved. Okay. So that's the first requirement you need to satisfy at the formal level. The second one is that you need to have something that is charged under the symmetry. Okay, otherwise it's completely trivial. Like you need to have, the symmetry needs to act on physical states, no, on your Hilbert space. And this more formally is written in terms of requiring that this operator acts non-trivially on some gauge invariant charge local operator. So this, what I mean is that if I apply this operator on O, I recover something different. Okay, so something changes. Okay, so that is something that is charged. Now this OX is what creates, like for instance, if I have some ordinary symmetry, this is the operator that creates the particles that are charged under the symmetry. Creates charged particles. Okay. And then the third criterion typically is that it satisfies some group law. Okay. Now we're gonna see how also this can be generalized, but this is like the basic definition of a global symmetry. Now, let's make one example. So the example, take blue. So the example is just one scalar field. Okay, so if I have some scalar and I don't have a potential, right? I have some symmetry, which is the shift symmetry of the scalar. Okay, so I can shift phi by some constant, and the Lagrangian remains the same, right? Now, this means that I have some global charge, which is the integral of the current. This is another's theorem, which in this case is the star of d phi. Okay, so this is the current, another current that is associated to this shift symmetry. And this is a current which is conserved because if you compute the derivative, this is 0, okay? Okay, and this conserved charge indeed doesn't change if I shift phi by a constant. So this is a conserved current. This is just a continuous V1 global symmetry. Okay, now the topological operator I was talking about is just the exponentiation of this charge. Okay, so this is the topological operator. You can write it in this case as the exponential of the integral of the current, which means that it's the e to the I alpha star d phi, and this is integrated over a codimension 1 surface. Okay, so this is the topological operator, and this is a global symmetry, and the operator which is charged would be the exponential of IQ phi, and this creates a particle. So it's a particle with charge Q. Okay, so this is an exact global symmetry. So the message is that this cannot be exact in quantum gravity. So we must either break it at some high energy scale or we must gauge it. Now, if we break it, then, so break it, there are two options. So break it means that I need to add something to the Lagrangian such that the conservation of this current is different from 0. For example, I can add some scalar potential, right? This is going to break the symmetry. And then, because then now when I compute, right, by Nether's theorem, the equation of motion and so on, I'm gonna have here the derivative of the potential, I mean, respect to phi, and it's going to be, it implies that the symmetry is not conserved anymore, of course, right? Now, quantifying how much I break to the symmetry is like putting constraints on the possible potentials that arise. And that's what I was saying before, that at the very least, it seems that we are gonna have some exponential, like at the very least, this has to go exponentially on phi, okay? Okay. The other option is to gauge it, which means that I need to introduce some new degrees of freedom to gauge the symmetry. That's what you learn typically in QFT, right? You add now some gauge field. So we add some gauge field, A1, so that my Lagrangian now is we have to add the coupling of the gauge field to the current and some kinetic term for the gauge field. Now this, when you write the current I put you before, this is just the typical covariant derivative, right? E phi minus A squared. Okay. Now this symmetry now is gauged, right? Because what it means, let me add one page. What it means is that now the theory is invariant under the combined transformation, right? Of phi plus lambda x. So now we can promote this to even a local quantity. Okay. A minus d lambda x. Okay. So now the symmetry is gauged. And I have two types of transformations. If lambda when this goes to infinity, goes to 0, or if you want like this lambda depends on x, this is a gauge transformation, is a redundancy. But if lambda, I consider the subset of cases in which lambda is a constant, this is actually something that is physical. It acts on the Hilbert space. And this is what we mean that this global symmetry, this is the global part of the group, the global symmetry is gauged. Okay, so the transformation by a constant is now part of this larger gauge group. It's associated to some gauge degree of freedom. And the symmetry is not purely global, it's gauge, and therefore is consistent with quantum gravity. And if you want to write it also in terms of the currents, what happens is that if you compute the equation of motion, now you find that the current that we had before for the field is now an exact current, and that's equivalent to say that it's gauged. Okay, whenever the current is exact, means that the symmetry is gauged. Okay, any question? Okay, very good. So this was one example. Now, the power of this constraint, this conjecture of absence of global symmetries, is that it applies to any type of global symmetry that you could have. And recently, there has been a lot of activity also generalizing the notions of symmetry. So, and that implies that actually, when you apply these conjectures to all these new types of symmetries, you can really get constraints that are relevant and highly non-trivial, even before quantifying how much you break the symmetries. Just the statement that they cannot be exact. So just to finish this part, and then we can take a small break. So the point is that recently there has been many generalizations. So we have all these generalized global symmetries, or p-form global symmetries and so on, which generalize the fact that now these are the three criterion that I gave you before. Okay, so this was U topological, right? And here we had this condition that acts non-trivially on some operator. Okay. Actually, let me also, so just to make it clear, so if we don't satisfy the first one, right? If the first one is not satisfied, it means that the symmetry is broken because it's not conserved anymore. Meaning that it's gauge, what happens is that we don't satisfy the second one because now all the operators that are charged under the symmetry are not gauge invariant anymore. Okay, so that's just to make it clear. Okay, but as I was saying before, so the point is that we can generalize this to many new types of symmetries. So these are all these p-form global symmetries, which the generalization comes from saying that this lives in a higher dimensional manifold, so that the objects that are charged under the symmetry are not local operators, are higher dimensional operators, meaning that the physical objects are higher dimensional states. So this operator creates a higher dimensional charged states. So instead of having particles that are charged under the symmetries, now you can have strings, membranes, higher dimensional objects that are charged under the symmetries, and therefore, and whenever, for instance, if I have a string which is charged, like a charged string, is associated to a one-form global symmetry, and so on and so forth. Okay, so particles are zero-form global symmetries, strings, one-form global symmetries, membranes, two-form global symmetries, and so on and so forth. Okay, so this is a generalization that is very important now. And the point is that all these new higher form symmetry, like p-form global symmetries, they should not be exact. And that's interesting because, for example, if I have some gauge theory, for example, I have some gauge fields, okay? I have now 1/4 global symmetries associated to these gauge fields, which are like shifting the gauge fields by constants. Okay, it's like very similar to the previous one. And the way to break these symmetries now is to introduce actually some charge states. So this is just one comment, and we'll go to the break. The point is that this would be like the current of the higher force symmetry, and this is broken if I have electrons. So requiring that you break all these higher force symmetries, like to break higher form, in particular one form symmetries, is equivalent to require that you need to have states that are charged under the symmetries. So you need to have the existence of charged states, which is also what sometimes is called the completeness hypothesis. So what you are learning from this is just like a comment, is that requiring that there are no global symmetries in quantum gravity is not only requiring that you will have like some new physics that the symmetry are high energies, it also requires to have, for every gauge field that you have, you need to have something charged under it. So if you have a pure gauge field that's not consistent with quantum gravity, you need to have electrons. Okay, and electrons you need to have, I mean, for non-abelian gauge fields, then you need to have, sorry, you need to have particles in every possible representation. So you start observing something that we observe in the string theory, which is that everything that you could have, typically you have it. And this was something, it was like an old, I don't know, common law in string theory. Whenever you have some gauge field and so on, you always have something charged under it. It seems it's unavoidable. The more recent understanding is that you need to have always things that are charged and so on to break any possible symmetry. And there are many things, there are many words that we are trying to understand what new objects you can predict, with new particles you can predict they must exist to require the absence of global symmetries. And by playing this game, like for instance in string theory, there are many people that are working on reproducing like the existence of branes, new non-supersymmetric defects, many things that are much more technical, and I'm not gonna enter to. But yeah, like the message is that you can try to reproduce what is the spectrum of the theory that you have, just from requiring the absence of global symmetries. Okay. Okay. Any question?
So means how many new particles means they are going to be generated? That depends on the previous theory we are working on, because new particle or new field, that will depend on the number of generator brokens.
So you are the point is that you need to have a state for in every possible representation in order to completely break all the higher form global symmetries. So you have to study the possible representations, right? Depending on the algebra that you have, and that are consistent with Dirac quantization and so on. And then for every possible representation, you need to have a particle. I'm not telling you still what is the mass of the particle, just telling you the mass exists. And the mass will be associated to how approximate the symmetries can be. Okay, that we'll discuss later about this.
So given the energy momentum tensor, how will I find this operator, local operator?
Say again, can you repeat?
I want to find this operator U. How will I find? Means then I have to check which operator is going to break this symmetry.
As I say, like to break, like it depends what symmetry we're talking about. If you think of ordinary symmetries, then you're gonna have a new operator in your theory that breaks the symmetry, and then you have to quantify the size of the operator, which, as I was saying, at least will be exponential. So you will have like something, it's an exponential separation in terms of the cutoff. That's for ordinary symmetries. The way to break 1/4 global symmetries is not to add some operator to your theory, is to add some physical state. So depending what symmetry we're talking about, there's something different that you have to add. Okay, and then you can try to reinterpret, like, I don't know, why, for instance, we have this type of fermions in our theory. maybe there is a quantum gravity reason because you need them to have to break the global symmetries and so on and so forth. But it depends what symmetry we talk about. The answer will be different. I mean, it's not universal. Okay. Okay, let's take a 10 minutes break or 5-10 minutes break. Okay, so so let me summarize and then ask if there are questions, and then we can move on to the next topic. So we've seen one of the most important Swampland criteria, which is the absence of global symmetries. They must be gauged, which means that you have new degrees of freedom, or they must be broken, which means that you need to have some breaking effect. And depending on what type of symmetry we're talking about, it's going to be a different one. And you can try to extract what are the possible implications depending on its symmetry and so on. Like for example, I give you just the simplest example, which is some shift symmetry for some scalar, because for instance, the shift symmetry is something very used in inflation, right? Like whenever you want to have also small parameters, you always assume that maybe there is some exact symmetry in the UV, which is only a bit broken, and then you can control the dynamics. All these things are problematic in quantum gravity because global symmetries cannot be exact. You have minimal breakings. And whenever you hear about some approximate, very nearly exact global symmetry, you should worry about. Okay, that's the message. Now, I also show you that even if we don't have much time to discuss this, but there are many generalizations of global symmetries, which is very interesting because we need to get rid of all of them. So the more the better, the more we learn from the absence. And they are higher for symmetries, many things that you might study in the future. They are all problematic in quantum gravity, okay? And requiring all the breaking of these higher force symmetries recovers a lot of the structures that we actually observe from string theory, like the existence of extended objects, branes, charge states, many things, okay? There is also another generalization that I forgot to say, which is that this third condition, you can actually also violate it. And this is what is called a non-invertible symmetry, just for you to know. This is another generalization of global symmetries. These are also global symmetries because they are still described by topological operators, so they are also problematic in quantum gravity, and there are also phenomenological implications that appear from requiring the absence of all these non-invertible symmetries. The whole point is that whenever you have some symmetry in terms of some topological operator, then something must break it, because actually in quantum gravity, the topology can change. Topology can fluctuate in the same way that in classical mechanics, in classical Einstein gravity, geometry changes, right? Like geometry is not something fundamental, it changes with the masses. When you promote this to the quantum level, what happens is that it's not only that geometry is not fundamental and can change, the topology of the space-time can also change. And that's why all these topological operators that describe global symmetries are not conserved anymore. Okay, any question?
Yeah, I would like to ask about the relation or the statement between like breaking this global symmetry and having chart operators. So can you explain a little bit about what is the relation and why? I mean, if you break the global, then you have chart operator, and in terms of representation. So why chart operator means that in each representation you will have some particles.
Okay, good.
Like
so let's take the example, some gauge field, okay? I have this, what is called this U1 form, global symmetry, which is just shifting the gauge field by a constant, okay? If I only have the pure gauge theory, this is a symmetry, okay? This is conserved. And the current associated to it, the current is the field strength of the gauge field. Like if you apply another theorem, you can compute as an exercise that this is the current.
So we're talking about SU2, right? Or SU1?
About what?
SU1.
Now,
we're talking about SU1?
Right now, exactly, I'm doing U1, okay?
U1.
Then I generalize, exactly. So for the U1, you do this, and then you see, okay, by the equation of motion, we know that precisely the equation for the conservation of the current is equal to the equation of motion for the gauge field. And this is different from 0, right? Whenever I have charged matter, which means that the symmetry, the 1-4 global symmetry is broken whenever you have some electron that is charged under it. Now, if you promote this now to some non-abelian gauge theory, like any general, right, beyond U1, you can still define these 1-4 global symmetries. Now they are going to be labeled, so the topological operator is labeled by the conjugacy classes of the gauge field. So you have some current labeled by that. And then this is the proof. You can find it in a paper I have, which is called like, I don't know, completeness and non-invertible symmetries, I think it's called. There we prove that in order to get rid of any, the full 1-4 global symmetry, because now the 1-4 global symmetry is gonna belong to the what is called the center of the group. So in order to get rid of or completely break the center of the group, you need to have charged matter in every possible representation. It's just you can prove it with group theory.
Charged matter, you mean? Okay.
Yeah,
And
I mean,
what is a charged matter in a representation? What means this?
so representation, I just mean like you have a gauge theory, right? You can compute without the possible representations. For a U1, it's just the integers. You can have quantized charge for charge 1, 2, 3, 4, 5, so on. For a non-abelian theory, you can have different representations. Like you can have, I don't know, they can live on the adjoint or the fundamental representation, right? And then the point is that you need to have some state in every possible representation, states in the adjoint, states in the fundamental representation, and so on, to break all the symmetries. Because otherwise, what happens is that you break part of the 1-4 global symmetry group, but there is some remnant that remains, like some discrete remnant, and so on.
Okay.
And then this is something that you can prove easily for continuous groups, but we also prove it in general for any possible, even disconnected or discrete gauge group. But then you also need to enter into all this discussion of non-invertible symmetries and so on, because there are non-invertible symmetries there. Any other question? Okay. So that's it for exact symmetries. Now, of course, the important question that comes afterwards is how much you break it, no? How much you gauge it. What about approximate global symmetries? Now, this is, I mean, the rest of the Swampland conjectures are basically trying to quantify this in different ways, okay? Depending what symmetry we're talking about and so on. Even if originally sometimes they were not formulated in that sense, but nowadays what we understand is that they can all be correlated to obstructing somehow, restoring some global symmetry. Okay, so what goes wrong if I try to engineer a global symmetry in the sense that I have it's not exact, but it's nearly exact, it's approximate, okay? What goes wrong, like what's happening? Now, this is difficult to answer in general, but from string theory, we have a very clear picture of what's going on. Okay, so let me explain what's going on, because this is going to be useful to motivate the weak gravity and the distance conjecture, which were motivated from string theory, even if we now have evidence beyond that. Okay, but it all started from string theory, so let's follow this path. So, for example, imagine that we have gauge the symmetry, so we have a gauge field, but the gauge coupling is very small, right? So what happens if the gauge coupling goes to 0? I'm going to restore a global symmetry. So you could ask, okay, how small a gauge coupling can be? Okay, so this tells me how approximate the symmetries are. Okay, so this is just to take an example. Like, I mean, you can imagine changing the parameters in your EFT such that you engineer some approximate symmetry, like for instance, by having a very small gauge coupling. Now, you can think of having like the space of parameters. Okay, so have some space of parameters. Let me plot it like this. Each point means I have a different value for the parameters, like a different value of the gauge coupling and so on. And then you can ask, okay, what happens if I move whenever the gauge coupling becomes very small, for instance? Now, the point is that doing this in string theory is equivalent to moving in the field space. So the point is that in string theory, there are no free parameters, okay? In the sense that any parameter like couplings, masses, any parameter that you might have in your EFT, it's actually given by the vacuum expectation value of some scalar fields. The same that with the masses for the fermions and the Higgs, okay? So the point is that, for instance, a gauge coupling is gonna be given by some vacuum expectation value, some scalars. So changing the value of the parameters is like changing the vacuum expectation value of the scalar fields. So moving in this space of parameters is like moving on the field space, like changing the value of the scalars, okay? Now, these scalars are in string theory, they tell you, they parameterize the size of the internal dimensions, the volumes, the shapes, all these geometrical quantities. Like you have string theory, you will maybe learn at some point, string theory lives in higher dimensions. So to connect with 4 dimensions, you compactify. And then you have many scalars that arise, which are parameterizing all these volumes and so on, or the geometry of the internal dimensions. And this is what parameterize, this is what gives you all these, the value of the parameters of your EFT. Okay, so what goes wrong? Like what happens in string theory? I mean, string theory is a consistent theory of quantum gravity, so you can ask directly, you can go and check. What happens if I try to move to some point in which I would restore a global symmetry? And then the answer is that whenever you try to do that, what happens is that this point in which you would restore the global symmetry is pushed to infinite distance. Like the global symmetries are never restored in the middle of the field space, but are pushed to the boundaries, like to the infinite distance boundaries. So you never get there. So you never restore the global symmetries because you don't have global symmetries in string theory. Okay, so global symmetries can only be restored at infinite distance in the field space. Okay, and not only that, there is some universal physics that arises when you go to this infinite distance. What happens is that as you move towards these boundaries in which you would restore some approximate global symmetry, like for instance, a gauge coupling goes to 0 or something like that, then the cutoff of the EFT, the scale at which the EFT is not valid anymore, goes to 0. Okay, so this is what we call the quantum gravity cutoff, in the sense that it's the scale at which the EFT cannot be completed in QFT. Like really quantum gravitational effects become important. Okay, you really need to complete the description in a quantum gravity theory. So what happens in all in string theory is that if we try to restore a global symmetry, this implies that we need to move to the infinite distance boundaries of the field space, and then there is going to be new physics that arise that force this quantum gravity cutoff to go to 0, because there is new light physics that arise. Okay, so the EFT stops being valid. And of course, it goes to 0 when you restore the symmetry, so there is no theory to talk about. But also, if you are very close to restore the symmetry, what happens is that the cutoff of the theory is very low. Okay, and that's why you have like a continuous obstruction, this works in a continuous way towards restoring the symmetry. So let me write it down to be clear. So the point is that the EFT breaks down when approaching these infinite distance points, okay? Because actually what we find is that, and this I will describe in more detail, because there is infinitely many new fields that arise. So you cannot just consider this in QFT. There is infinite, like an infinite tower of states becoming light. And that's this forces the cutoff of the EFT to go to 0.
So
Okay.
the
Yes.
symmetry which we know that they are global, for example, B minus L symmetry. What happened to that symmetry?
Which one? B minus L, you said?
Yeah, baryon the difference between
Baryon
baryon
minus lepton?
B
Well,
minus L, yeah.
we know that the symmetry must be either broken or gauged, which means that either there is a new gauge field, like a new force, some dark photon or something that is associated to B minus L, and therefore is exact, or there is some effect that breaks the symmetry, right? There's new operators, new dynamics in the UV that break the symmetry and can have an impact in baryogenesis and so on. Now, what I'm saying also, what we are saying now is that how much you break the symmetry or how small this new gauge coupling is going to be associated to what is the cutoff of the EFT. In the sense that, imagine that we say that B minus L is gauged, okay? So there's a new field that gauges the symmetry. If I want this, this new field, it has to be very quickly coupled because otherwise we had already detected. But the gauge coupling cannot be super, super small because the smaller it gets, the smaller the cutoff of the EFT is going to be. Okay, so now you have a constraint. And let me write it here. So what we are going to see is that the cutoff behaves as the gauge coupling times M Planck, or like when I write in terms of gauge coupling takes this form, or when I write in terms of the scalar fields, it goes exponentially on the scalar. Okay, so this means that even if you think that the quantum gravity effects are only important at the Planck scale, that's not true. If I have some gauge couplings, the quantum gravity effects, the quantum gravity cutoff, okay, is of order the gauge coupling times M Planck. So if the gauge coupling is small, this can be much smaller than M Planck, right? So if I want to add now some new gauge field to my beyond standard model, like for instance, that gauge B minus L, I have a bound on how small, how weakly coupled this new field can be, because the cutoff has to be at least of order the TV, because we have not detected quantum gravity effects at the LHC. So you at least you want the EFT to be valid up to the TV scale, and that puts a constraint on how small this gauge coupling can be. Okay. And that's why I was saying that small gauge coupling, large field distance, they are problematic in the sense that they reduce the cutoff. So if you want your theory to be valid at a very high energy scale, then you cannot have a small gauge coupling or a large field range because you are too close to restoring a global symmetry. Okay, so this, and now we're gonna see this in more detail. This constraints is what is called the weak gravity conjecture. This comes from the weak gravity. And this is what is called the Swampland distance conjecture. So what I'm going to do in the rest of the time is to formulate these two conjectures in more detail and see why, right, like why this behavior arises. Okay. So let me start with the distance conjecture, which is like, understanding what happens when you move to the infinite distance of the field space. So we write the relation between the cutoff and the value of the scalar fields. Okay, so the conjecture is that there is an infinite tower of states becoming exponentially light at every infinite distance limit of the field space. Okay, of the field space. So that the mass of the states, like if I have, I don't know, some moduli space, and I move some point Q, and I move to some point P, which is approaching some infinite distance boundary, mass of P behaves exponentially in terms of the mass at Q, in terms of the geodesic distance that you traverse in this field space. Okay, so this is if I have some theory at Q, okay, I have some EFT, and if I now have some displacement of the scalar fields, the point is that the EFT gets modified because I get a new infinite tower of states whose mass behave exponentially in terms of this scalar field variation. Okay, as this is a parametric statement, so this happens as delta phi goes to infinity. Okay, and this delta phi is the geodesic distance. So when you have more than one field, the proper way to formulate this is that you have to consider what is the scalar manifold, taking into account the metric coming from the kinetic term, and then you compute the geodesic distance from that. Okay, now, since we are talking about an infinite tower of states, this implies the complete breakdown of the EFT. If it was just a finite number, you can just integrate in the new field and have a new EFT, and that's fine. But since it's an infinite tower of states, there is no way to have a quantum field theory description, a local quantum field theory description anymore in the same number of dimensions. So that's why we say that this is like the quantum gravity cutoff. Something drastic happens. Okay, there's a new change of the theory. And then this quantum gravity cutoff, well, behaves exponentially on the field distance. Okay, now, I didn't tell you here what is the exponential rate. So the conjecture originally only said that it's exponential, but nowadays we have a much better understanding of this conjecture at the quantitative level. Okay, so this alpha, okay, this exponential rate, there is a proposed bound, which is 1 over the square root of d minus 2, where this is the number of space-time dimensions. Okay, this is the dimension of the space-time. And this bounds comes from string theory. Okay, so this is right now this bound is just motivated from string theory. Okay, we need to understand if it's general or not. Okay, and it comes from the fact that the exponential rate gives you information about the nature of the tower. So what are these states? Okay, if the bound is saturated, then you have string modes, like you have string states that become light. While if the value of alpha is bigger, what you typically have is a tower of particles. That whenever you have an infinite tower of particles, what this signals is some decompactification. So what you have are extra dimensions. Okay, to higher dimensions. Now, this conjecture, as I said, was motivated from string theory because every time you go to an infinite distance limit in string theory, you always find these towers of states that become light. And from checking many compactifications, so far the only two types of states that we have found are either string oscillation modes or particles like Kaluza-Klein particles associated to extra dimensions, and that's what gives rise to this bound. Part of this is a bound that appeared last year. A lot of ongoing research comes from understanding how general this is. Okay, like try to see if we can give some argument beyond string theory. Okay. For example, so let me say why this is useful. So what I'm telling you is that there is a correlation between the cutoff, right? So the message is that there is a correlation between the cutoff of the EFT, which signals a new infinite tower of states that become light, and the scalar field variation. Okay. Like the cutoff in field space. These are two quantities which in principle in QFT are not connected. Okay, you could move very far away, like for instance in inflation, you have a variation of the scalar fields, and you can have a large excursion. In principle, it's fine as long as all the energies remain below Planck. But what this is saying is that if you have a very large excursion, then you're going to have a very small cutoff. So what this is putting you is an upper bound on the field range that a given effective field theory can accommodate before quantum gravity becomes important. Okay. So the higher you want the cutoff to be, like for instance, inflation, if you want to have Hubble scale to be very large, then this puts a constraint on how large the scalar field can be. And this puts, for instance, constraints on the tensor to scalar ratio that we detect for gravitational waves and so on. And you can use this to rule out or to constrain different models of inflation or beyond standard model. Okay? So it's an upper bound on the field range. And that's why it's very important to understand very well what are these factors, this exponential rate, because to have a quantitative bound, we need to be precise about all these exponential rates. Okay.
I'm sorry, I have a question. In the previous slide, you defined the delta F as a geodesic distance of the field. I know what is the geodesic in any space science, but what is a geodesic distance for a field?
Yes, very good. Let me explain it in case it was not clear. So imagine that you have your Lagrangian, and I have more than one field. Okay, so what happens is that I have some field metric. Okay, which is not a space-time metric. So apart from this, right, you can have like you have the field metric, okay, in the space-time. But the point is that you have a field metric which comes from the kinetic term, which just tells you how the matrix, no, of all the different scalar fields and so on. Now, this field metric of the kinetic term is what you use to define a metric in this scalar manifold. So now you can see that these phi are your coordinates. You have some scalar manifold, like I don't know, phi 1, phi 2. These are like different coordinates in your scalar manifold. And this kinetic metric is a metric in this space. So to compute the geodesic, okay, you just compute, right, the geodesic distance using this metric that you read from the kinetic term. Okay. So this is the geodesic distance. Any other question? Okay. So here I could give many different examples from string theory, but since I don't think you know much about the string theory, I think there's not much point into entering into all these examples. I'm just gonna tell you one which maybe you already know, or like, I don't know, or it's useful to know just to have an example of what these towers are. But yeah, I mean, like there has been a lot of work like trying to check in different compactifications what are the towers, identifying why they are there. And this has actually been very useful to understand better the geometry of the string compactifications, because the existence of these towers has also pointed out to some universal geometric structures that arise. And I don't know, there are, so sometimes you use string theory to learn about the Swampland program, but sometimes these Swampland conjectures can also be used to learn about the string theory itself, because they tell you where it's interesting to look to find some universal constraints. So just to give one example, and then we go to the weak gravity conjecture. It's very common to talk about the strings is more complicated. So let me talk about the second case, which are particles of extra dimensions. So whenever you have extra dimensions, when you have, like, for instance, we have some theory, have a theory in d dimensions, okay? And we compactify the theory on a circle. So we get a new theory in d-1 dimensions, okay? This is something that you do a lot in string theory because what you do is indeed like to compactify some dimensions, so they are compact spaces, and therefore they can be small, and that's why you have not detected these spaces yet. So when you do that, you're gonna get tower of states that appear whenever the volume becomes very large. Okay, so the theory, let me put it here. So this low energy, imagine that now we don't know that we come from extra dimensions. You just have information about the lower dimensional theory. Imagine that is our universe. You have some Lagrangian, and you have some scalar field, which actually parameterizes if you know about it, it's going to parameterize the size of the extra dimensions. But from the low energy perspective, you have no idea. It's just some scalar field, okay? Now, the point is that whenever this field becomes very large, what this distance conjecture is telling you is that you need to have a tower of states. And indeed, you can understand that this tower, when you have the UV completion, is the Keiki tower. So you have Kaluza-Klein, that are called Kaluza-Klein copies, right? That become light whenever this field becomes very large. So whenever the volume of the circle becomes large. And well, if you compute it in detail, you get that this goes exponentially in terms of the canonically normalized field, d minus 1 minus 2. Okay, so you can compute exactly the exponential rate and everything. And these are Keiki modes. Okay, so this happens when phi becomes very large, because then you decompactify the extra dimension and then you get all these new towers of states. Now, when you go, yes, please.
So when you compute the geodesic distance, it seems it depends on the metric, but not on the field.
No, but the geodesic distance is a quantity which is invariant under diffeomorphism. Okay. Now you compute in terms of the metric because these are coordinates, so that's how you get something that is invariant.
Oh.
Like, right? Like if I just tell you that the distance is delta S or I don't know whatever coordinate you have, that's a coordinate dependent statement, doesn't have any meaning. That's why you have to integrate together with the metric, which is also coordinate dependent. And then the result, the geodesic distance, is a physical thing. It does not depend on the coordinates. It's invariant under diffeomorphism. So it's something physical. And if you want, it's equivalent to put this in the canonically normalized form. So when you compute this distance, what you're gonna get is that your Lagrangian is just the phi square, like the new, or the delta phi, like the new field is just canonically normalized. Okay. So that's something physical. Okay, good. So, okay, so the only thing I wanted to say is that this is known in field theory that you get new states when the circle becomes large. But the point is that if the circle becomes small, this is also an infinite distance limit, and you also have new states. And then what happens if when phi goes to 0, you can also see that this is at infinite distance if you compute the geodesic distance. And then you need to have new states, and what you find are winding modes. So these are when phi goes to 0, and otherwise what you find are what are called winding modes, which are actually extended objects that wrap the circle and become small whenever the volume goes to 0. So even if you don't, this is something that happens in string theory all the time. Like you have strings and wrapping brains that become light when the volumes become small. But if you didn't know about string theory, if this conjecture is something general of quantum gravity, what it's telling you is that since we need to have a tower of states when the circle becomes small, we need to have some extended object that is wrapping the circle. So it's predicting the existence of extended objects in the theory. It's not consistent just to have a theory of particles. That's one of the consequences. Okay. So if we just think of one dimension, then you need to have at least one string that wraps one dimension. Otherwise, you can have higher extended states. So maybe you don't know much about the string theory, but okay, just you can learn from it from bottom up, like from these distance conjectures. We note that our quantum, to move this up, if this is a general feature of quantum gravity, we can already, even without having full string theory, we can already derive the existence of extended, like higher dimensional objects that are wrap extra dimensions. Okay. Okay, good. Any question? Otherwise, we move to the weak gravity conjecture. Okay, so just to finish, let's then focus on the third conjecture, which is also very important, which makes reference to what happens when the gauge couplings become very small. Okay, so instead of talking about the scalar field variation, now we're gonna describe everything in terms of the gauge couplings. Now, the statement, which was actually formulated independently of global symmetries, but now they are correlated, is that given a gauge theory, there must exist some electrically charged state with a charge to mass ratio, which is bigger than the charge to mass ratio of an extremal black hole in your theory. So this is some order one number that you can compute depending on what theory you have. And the point is that you need to have some state whose mass is smaller than the charge under the gauge field. Okay, so this charge is the physical charge, so it's the quantized charge times the gauge coupling. Okay. Now, I'm going to explain the motivation, the original motivation of the conjecture, which is based on black hole physics, not in string theory. But just to connect with what I was saying before, this in particular implies that since there is a new particle, I have a new cutoff, like the EFT breaks down at a scale which is smaller than this charge, so at least it goes as smaller than the gauge coupling times m Planck. Okay, so this mass is given in Planck units. That's why here I'm putting m Planck back. But the consequence of this is that the cutoff of my EFT goes to 0 if the gauge coupling becomes very small, because then I need to have very light particles. Okay, so if the gauge coupling is very small, then the mass has to be even smaller. Okay, and that's why it helps also as a quantum gravity obstruction to restore a global symmetry that would arise if the gauge coupling goes to 0, because then the cutoff goes to 0 as well. Okay. Now you could say that here, okay, the difference that it seems I'm only talking about one particle, but originally this conjecture was formulated by requiring the existence of a single particle, because that's where the black hole motivation comes from. But the current status is that you need to have not only one, so here, okay, it's not one, but you need to have infinitely many. Again, like an infinite tower of states satisfying this. Okay, so in the string theory, at least what we find is that the weak gravity conjecture is not satisfied only by one state, but by an infinite tower of them. Okay, or if you want, sometimes people say an infinite, like a sub-lattice or a lattice of charges. I mean, in the end, it's that you have infinitely many states satisfying this. And that's why this cutoff is really like a drastic breakdown of the EFT again. Okay, so this generalization to an infinite tower, this is motivated from string theory, again, motivated by string theory. While at least the existence of one state, we can motivate it purely from black hole physics, which is what I will do next. Okay, so what is the black hole motivation? Okay, I was telling you before that for instance, we can use black holes to to motivate the absence of global symmetries, right? Because we had this infinite entropy and so on. You can also try to use black holes to motivate how tiny the gauge couplings can be. Okay, so now if the symmetry is gauge, the previous argument is fine. So you should remember I gave you, this was the metric for the solution of a black hole. I put you at the beginning. Okay. And if it was a Schwarzschild neutral black hole, okay, if it was neutral, the problem is that this function only depends on the mass, right? R is just the coordinate, the distance to the black hole. And then we had infinitely many possible ways to do it. This was an infinite entropy and so on. Now, if the black hole is charged under a gauge field, then the horizon is sensitive to this gauge charge. Okay, so you can find, for instance, a Reisner-Nostrom black hole solution is called. Okay, so just for completeness, let me put the result. Point is that this, you can write it purely in terms of the mass, but also in terms of the gauge coupling, the gauge charge. Okay, this G is the Newton constant. So what I want to say, I mean, the message is just that the horizon depends both on the mass and the gauge coupling, okay, the charge of the black hole. And there is also what is called some extremality bound, in the sense that if you don't want to have a next singularity, so some singularity in the space-time which is not covered by some horizon, so you want to have a regular black hole, then the charge cannot be too large in comparison to the mass. So this is what is called extremality bound. So the mass has to be bigger or equal than m Planck. This is extremality bound. For black holes, okay, which is to avoid some singularity. Otherwise, the space becomes singular. Okay, so you could say, okay, this is, so I was saying, so this gives rise up, this is a problem with entropy, okay, because I have infinitely many. Now, if you compute how many different remnants, like how many different black holes I have, how many black holes I have below some energy range, like to see, again, if I get some violation with entropy or so on, what you have to do is to compute well, this is just like the number of states is related to entropy. Don't worry, you understand the details very well. It's just to make it explicitly. What I want to say is that since the charge is bounded by the mass, you have to sum only the possible black holes that you have in your theory. And if you do the computation, the point is that the number of black holes, of stable black holes that you have, it goes inversely proportional to the value of the gauge coupling. So that you can see that if the gauge coupling goes to 0, so you have a global symmetry, the number of black holes that you would have that are stable are infinite, and that's why you have a problem with entropy. But if the gauge coupling is very small, you can still have a very large number of black holes, and that can still be problematic. Okay? This is problematic if the gauge coupling is very small. Which is what we expect, because then you restore some approximate global symmetry. So what is the weak gravity conjecture? Well, the weak gravity conjecture is saying, okay, there is a way out, like how to, to forbid that you get this gauge coupling very small, is that maybe what happens is that these black holes are not stable, they decay, so there's no problem with them. And that's what the weak gravity conjecture imposes, okay? So the weak gravity conjecture is equivalent to the statement that you require that black holes are not stable. They can decay. So that even if you can construct many of them, they are not going to dominate any decay process because they are not stable particles. So if you have, even if you have infinite, well, not infinite, but like a parametrically large number of them, it's completely fine with entropy bounds and so on. So the weak
Yes.
gravity conjecture is the required. Just say sorry.
Yeah, you can. It means a black hole can radiate charged particle also, huh?
Exactly. So the black hole can exactly. So that's let me say. So the weak gravity conjecture implies that the black holes can decay. Okay, they can decay by emitting. Okay, by radiating some particle. And then you can ask, okay, what is the mass of the charge of this particle? That's precisely the point. Like you can study. So if I have some black hole, okay, if I have a black hole with a very large mass, they can always evaporate by Hawking evaporation. But at some point, they are going to reach this extremality bound. And then they cannot continue evaporating. And then they become stable, unless there is some particle in my theory to which they can decay to via the Swinger effect. So if I have some extremal black hole, this can become some smaller black hole, okay, with a charge smaller than the mass, only if I also have in my theory some particle, so that you can radiate this particle away, that has a charge which is bigger or equal than the mass. Okay, so this is some black hole, this is some particle, okay, and this is a particle. So in order to be able to have all the black holes decaying and radiating away, you need to have particles whose value of the charge is bigger than the mass. Otherwise, by charge conservation and energy conservation, this process is not allowed. And that's the weak gravity conjecture. Okay, you require that the black holes are not stable, and therefore you require the existence of some particles which has a mass smaller than the charge. Okay.
When the black hole is evaporating, there must be at some point, means when charge is less than equal to mass.
When charge is less equal than?
Means I am saying there will be a point when it will become a maximal black hole, means it will become a stable. It will become a stable.
I mean, so let's see.
Means if there will be a point when M will satisfy that this condition.
Okay, so imagine that we start with a very large black hole with a very large mass. First, this is going to evaporate by Hawking into something smaller. You lose the mass, but you don't lose the charge. So the minimal mass that you can have is when the mass is equal to the charge. And then you cannot continue Hawking evaporating. So the only thing, if you want to require that continuous decaying that is not stable, you need now to have a particle such that a charged particle, such that the black hole can emit this particle and then continue becoming smaller. Okay, and that's the weak gravity conjecture. Yes.
Just I'm wondering how this Coupling constant appear in the black hole. G.
G.
Yes.
So the
I mean, the entropy, because there is a sum over
here. Entropy. Yeah, you can do this as an exercise. So like if I so what I'm doing is to count like how many black holes you have below a certain energy range, below a certain mass.
Yeah, but my question is like the G, it's a coupling constant in the matrix. How it's appear, right? That's
because the physical charge of the black hole, this Q that I'm putting later, is the quantized charge times the gauge coupling. So now you can count the black holes, which have like different values for this quantized charge. Like this belongs to some integers.
This is coupling to what?
This is the gauge coupling.
Where is come from? Is from a string?
No. So what I'm saying is that now I have some theory in which I have some gauge field and gravity. And I construct black hole solutions that are charged under the gauge field. So that's why they have a charge, a physical charge that has some quantized charge times the gauge coupling. So they feel the value of the gauge coupling. They are charged black holes. In the same way that you can have charged particles, you can have charged black holes. Okay. And the problem is that, okay, charged black holes still, even if at the beginning they can radiate, at some point they hit this extremality bound and they will be stable unless you have some particle that is also charged under the gauge field to which the black hole can decay.
So it means weak gravity conjectures means it's not possible for a black hole to evaporate completely just by Hawking radiation.
No, you can never evaporate completely. You always reach only the extremality bound. Whenever you have an extremality bound,
then after that it will not radiate Hawking radiation.
It will not
but
radiate
something else.
Hawking. Yeah, you need a swinger effect. You need to radiate charge. You need to get rid of the charge because the mass can never become lower than the charge. So by Hawking, you don't get rid of the charge. You only change the mass.
But if the black hole is Schwarzschild, then means there is no charge in nothing. Then it can evaporate by Hawking radiation.
Yes, a neutral black hole that doesn't have a charge can always evaporate by Hawking evaporation. The problem is that the problem you have is what I described before, that now even if they have different values of the global charge, then they can be problematic. But for the gauge charge, it's completely fine. Yeah, it's like different things. Like a neutral black holes, they don't give you a constraint on the gauge field. Of course, it's fine. They give you constraints for global symmetries. While charged black holes, they give you constraints for the gauge field because you cannot continue evaporating. Yeah, it's clear?
Thank you.
Yeah, so let me be clear. So if you want to avoid the existence of infinitely many black holes stable in your theory, you need to require first that you don't have global symmetries, because then you will have infinitely many neutral ones. And then that even if they are gauged, which seems fine, they need to come together with some particles that are charged under the gauge field and whose mass is smaller than the charge. Okay. And that's how the weak gravity conjecture constrains, like, yeah, that you need to have mu states and constrains how small the gauge coupling can be and how approximate symmetries are. Okay, so yeah, let me just make a few more comments and we finish. Yeah, so this is the original motivation from the weak gravity. The cool thing is that, yeah, like for the weak gravity conjecture, you have different motivations and evidence coming from many different things. Like this is about not having stable black holes. From string theory is about just by checking the compactifications, you always find tower of states that satisfy this. From holography, you can also find some motivation. And all of them point to the existence of new states whose mass is smaller than the charge. Okay, and they are different motivations, like they are different evidence, but they all point to the same criteria. Okay, that's why we think that the weak gravity conjecture is a general feature of quantum gravity. And it's not clear what comes first. I mean, it's not clear what is more fundamental, what motivation is more important than the others. If the black holes, if the stringy ones, or holographic ones, but they all point in the end to the existence of these states. I want to make maybe one last comment, which is that here you can also think of the weak gravity conjecture. I mean, if the charge, right? If the charge is bigger than the mass, what means is that gravity acts weaker, right, on the particle than the gauge interaction. And that's why it's called the weak gravity conjecture, okay? Because gravity acts weaker. Now, whenever you have, so you could also phrase the weak gravity as the statement that the gravitational force smaller than the gauge force. Okay? Now, whenever we have other type of forces, the weak gravity gets modified. Then, like for instance, if we have massless scalar fields, maybe we have here also some scalar force. Okay, and then the constraint is different. Like you have that the charge is bigger or equal than the mass times something that depends on the scalars. Okay, this depends on the scalars. And the extremality bound gets modified and so on. So depending on the theory, you have to check, okay, what is the exact condition that you need to satisfy. And there's also a lot of research going on because sometimes the extremality bound seems a bit different than the condition of balance of forces when we go beyond weak coupling. At weak coupling, everything is the same. Beyond weak coupling is a bit different. So typically, this is called repulsive force condition as well. It's ongoing research to understand if this is exactly equivalent to the condition of extremality, of super extremality for the black holes. Okay. In general, whenever you have any type of force. Okay. Okay. So, any question about the weak gravity conjecture? Okay, so of course, as seems clear, the weak gravity conjecture is useful in general to constrain beyond the standard models that will have small gauge couplings, because then you also need to require the existence of charged states, which are very light. And maybe, I mean, with this, for instance, you can rule out models of milli-charged dark matter and things like that, because if the gauge coupling is too small, if this is too weakly coupled, then we should have already detected the particles that are charged under it. And that should also be very light. Okay, so you can play with this, and there are many papers also studying the phenomenological constraints and so forth. So just to finish the lectures, let's come back to the diagram that I put at the beginning. Okay. So we've seen these three statements. No global symmetries, the weak gravity conjecture, and the distance conjecture. What happens is that whenever we go to concrete examples in string theory, it seems that the same tower of states that satisfies the distance conjecture is the same tower of states that satisfies the weak gravity conjecture. So that's why they are related, because in practice, in the examples, we don't understand why, but in practice, in all the examples, it's always the same states. So we can talk about them in terms of the field distance, the scalar field variation, or we can talk about them in terms of the charge, but it's the same states. And that's part of the ongoing research on the Swampland program. Also try to see if we can find a better formulation of both conjectures, maybe that explains everything at once, why we always have these new states whenever we go to large field distances or small gauge couplings. Now, both, as I said, can be understood as obstructing, like some quantum censorship towards restoring some global symmetry, because the tower becomes light when the symmetry becomes approximate. Okay, so the cutoff goes to 0. So just to make it clear, the cutoff goes exponentially in terms of the field distance due to this new tower of states, or the cutoff goes linearly on the gauge coupling. Okay, in both cases, it's something surprising from bottom up, from field theory, because in principle, you could have constructed some effective field theory with a small gauge coupling, large field range. There is no problem. Now I'm telling you that you have infinitely many new states if you try to do that, whose mass is going to be proportional to these quantities. Okay. Now, the others, just to finish, so covariance conjecture I will not discuss. It's about topological generalization of no global symmetries. Completeness hypothesis, I did it even if you didn't realize, because we were saying that for the higher force symmetries, you need to have states that are charged under it. That was the completeness hypothesis. So now it's the same conjecture recently. And then the others, then you can ask, okay, when I have all these tower of states, what are the implications of the towers? Like even if I am at an energy which is below the mass of the new states, they can have some effect on the EFT, right? By quantum effects, like I integrate out the tower, and this has some effect. So what are the effects that arise from the tower of states on my EFT, like on the vacuum that I can have, or the scalar potential? Okay, and these are the other conjectures. Like you can see that there are some things that are difficult to generate, like non-supersymmetric ADS vacua that are stable, the CERN whenever you have approximate symmetries, like whenever you go to the infinite distance limits, or ADS vacua, in which you have scale separation with the internal dimension. So there are different conjectures that talk about the landscape of vacua that we can have, but they are all like consequences of having this tower of states. And the research comes from understanding, like whether we can formulate this better independently of the towers, if there is something fundamentally wrong with that, or what's going on. Okay. But the important ones, if you have to learn something from the Swampland program, is to learn about these three. Okay, this is the core of everything. Without this, everything falls. So I think I will finish here. Thank you all for listening, and I'm happy if there are more questions.
Yeah, thank you very much for your nice talk.